Hello everyone. Today we are going to derive the bending equation of the beam. So there are some assumptions for the bending equation. I want you to read those assumptions before you actually delve into the mathematics. Now, what is this bending equation? The bending equation is a very simple equation. It is given by the expression m over I is equal to sigma over I is equal to E divided by R. What is M? M is the bending moment. What is this capital I? It represents the moment of inertia of the beam. Remember, moment of inertia is resistance to bending. And what is the sigma? It represents the bending stress that is generated in the beam. Be very careful about the notation. Why? Because Y is not the deflection of the beam. Y is the distance from the neutral axis to the layer that you are trying to find the bending stress. Okay. For example, the neutral axis is represented by this dashed line here. And suppose you are trying to define the bending stress on this particular layer. So the distance Y is represented like this. So Y is not deflection. It is the distance from the neutral axis to the layer that you are trying to define the bending stress. Again, remember, this neutral axis is represented by this dashed line. This neutral axis is not the axis that actually passes through the center, but it is the axis that actually passes through the centroid of the beam. And please keep this at the back of the mind. Capital E is the Young's modulus, and a capital R is the radius of curvature. When I say the radius of curvature, at one point of time when this beam is subjected to load, the beam is going to bend in this fashion, and the radius of curvature is given by it is the radius, which means it is given by this distance. Okay, this is the center, and this is the radius. Okay, so that's the symbolic representation. Okay, now let us derive the bending equation in a step-by-step methodical manner. I'm going to get into the mathematics, but I highly recommend the readers to read the Euler's assumptions, the pure bending theory assumptions, before you actually do the mathematics. Okay. So to begin with, let us consider a beam. So let me represent this beam. So let us imagine a simply supported beam that is subjected to a uniformly distributed load. Okay. Now, because this beam is subjected to uniformly distributed load, what actually happens is the beam is going to bend in this fashion. Now, what I will do is I am going to represent the bending of this beam in two slides. In one slide, I am going to draw the magnified view of how this beam would look before it bends, and in the other slide I'm going to represent how this beam would look if you just localize your attention in a small region of this beam, how this beam is actually would look when it is highly amplified, and how that view would look like. So I'm going to do that. So here we go. So this is how the beam would look like if it is not bending, not at all a surprise. Okay. And I'm going to represent the neutral axis by this white dashed lines here. Okay, this is not a surprise. Of course, the beam is going to look perfectly straight because it is not getting deflected. Fine. Now I'm going to consider a layer at a distance y from the neutral axis. So let me do that. So if I'm considering a layer at a distance y from the neutral axis, I'm representing that layer by this yellow line. Let me call those edges A and B. Similarly, I'm going to drop a perpendicular, be very careful, so that it meets the neutral axis, and I'm going to call those lines N1, N2. That's right. And I'm also going to consider two layers below. I'm going to consider a layer below the neutral axis. So this is the layer I'm going to consider below the neutral axis. So the below the neutral axis, the layer that I'm considering, it is represented by the notation C and D. All right. So let me repeat this. I'm going to consider 2 layers, in fact 3 layers to be very precise. The first layer is the layer above the neutral axis. Let us say that it is at a distance y from the neutral axis. Just for clarity, this distance can be y, because the distance from the neutral axis to the layer that you are trying to define the bending stress, it is y. And let me say this for clarity. Let us also assume that the distance from the neutral axis to the layer that you are considering, and that is also y. Okay. So AB is the layer above the neutral axis that you have considered, and CD is the layer that you have considered below the neutral axis. Now, what is going to happen when the beam actually bends? So I'm going to represent that here. So when the beam is actually bending, the beam sort of bends when it is subjected to a load in this fashion. I'm not actually very good in drawing diagrams, so please excuse me if this diagram looks terrible. Anyway, I think I can still get across the concept. Now the question here is, what is going to happen to the layer AB, which is represented by the yellow line, and what is going to happen to the layer CD, which is represented by the blue line, and what is going to happen to the layer, white layer, that is N1 into that white layer that is right on the neutral axis? What is going to happen to that layer? Okay, now what is going to happen to the layer AB? The point A that you see here, I'm representing that, it gets shifted to the right, and the point B gets shifted to the left, which means that the layer AB is getting contracted. So the sum and substance of what I'm trying to say here is that the layer above the neutral axis is getting contracted. And what about the point CD? The point C gets deflected to the left, and the point D gets deflected to the right, which means that the layer below the neutral axis, it's getting expanded. Okay. Now you may ask me this question, whether this is actually true. I can give one example. So let us say that you are standing here, and when you are standing here, and what you are going to do is you are going to bend to pick up an object. Okay. So when you are bending to pick up this object, so here we go. So that is you are bending to pick up this object. Now your back actually stretches. This white, you see, actually stretches. Well, that should be represented by yellow, to be very precise. The yellow actually stretches, right? And the blue, your stomach, your belly actually gets compressed. If you want, I think that is quite intuitive. If you still have it out, maybe you can try it now. Your belly gets compressed and your back is getting stretched. So for exactly the same reason, okay, for exactly the same reason, I think I misrepresented the colors here. I think the color here should be this one. Just 1 minute. Let me represent the colors correctly so that it doesn't lead to any confusion. So okay, so the neutral axis is this. Okay, whatever is getting stretched, your back is getting stretched. In this case, that should be represented by blue, right? And your belly is getting compressed, so that should be represented by yellow. That's right. That's right. If you want to, so this is convexity is at the top, but here concavity is at the top. In the case of this beam, the concavity is at the top. Okay. Okay. Now let me represent that here. So here the new position of the yellow would be like this, and the new position of the blue would be like this. Okay. So the blue is getting stretched, the yellow is getting compressed. So I can see that there is a curvature, which means that I can now define the radius. So the radius of the beam is represented like this. They meet the center here. So this is the radius. Now I have to be very short, I'm precisely defining radius. It is the distance from the center, I can call this as O, to the neutral axis. So it is from this distance to the neutral axis. So that is the radius. So I'm precisely defining what is the radius here. All right. So this distance is going to be y. We know that we have already defined that distance is y. Now the new position of A and B is now represented by A dash and B dash. Similarly, the new position of C and D, this is going to be C dash and D dash. Okay, now I can define this subtended angle here, and that is going to be theta. The subtended angle, that is going to be theta. I can define for the layer C dash D dash, and also for the layer N1 and N2. Now there is something intriguing that is happening here. What we talked about the layer AB and we talked about the layer CD, but if you try to measure it practically, what is going to happen to the layers N1, N2? It is neither getting stretched nor getting compressed, which means that is the neutral axis. That's the reason why we say that it is the neutral axis. It stays the same. It is not getting compressed. It is not getting elongated. It just stays exactly the same. It is the neutral axis. All right. Now, can we try to define what is the length N1, N2, right? Because it is not changing its length, I'm not changing the notations. It just remains the same, N1, N2, which is now a curvature here, which is an arc here. And you know, for a circle, the arc length can be represented by the radius and the included angle. So it's r into theta. All right. This is true for a circle. If you want to try to define this arc length N1, N2, then it's the radius and the included angle. I'm just pulling the same trick here. It's the radius and the included angle. Now the point here is, initially the length AB is also equal to here. Here you see, here, the length AB is also equal to N1, N2, and it is also equal to CD. So we can now say N1, N2 is equal to r theta, but that is also equal to AB, and that is also equal to CD. We will keep this equation because it is going to help us do this mathematics. All right then. Now, what about the layer C dash D dash? I mean the arc length C dash D dash. How do you represent that? Again, it is the same. It is the radius into the included angle. So I will say it is the radius into the subtended angle, theta. But this time, what is the radius? It's not r. It's r plus there is an extra distance, which I can represent that by this red color here, y. It's r plus y. So it's r plus y into theta. So that is the new arc length C dash D dash. All right. Now that is the new arc length. Now the next question is, what is the old arc length? What is CD? What is the previous arc length? It is simply r into theta. Just borrowing that information from here. Now I have the old arc length, which is r theta. I have the new arc length. Now, which means that I can define something called as change in length. I can also define the strain, which is change in length divided by original length. That's possible. So in the next page, I'm going to do just that. So I can define something called as the change in length, which is the previous arc length, old minus new, which is going to be CD difference C dash D dash. I'm just bothered about the magnitude, so I'm not putting a negative sign there, divided by the original length, which is CD. In this case, it's going to be R theta difference R plus Y into theta divided by R theta. In this case, it's going to be R theta difference R theta difference Y theta divided by R theta. These two go away. You will be left out with Y theta divided by R theta. You'll be left out with Y by R. So I have got a beautiful expression. That is, I have got an expression for strain, which is Y divided by R. Having defined strain, I can define something called a stress, which is Young's modulus into strain. So stress is equal to Young's modulus into strain, which is Y by R. So I can rearrange this equation. So I can say sigma by Y is equal to E over R. This is the first part of the bending equation. I will call this as star expression 1. Well, we have completed the first part. We have derived the first part of the bending equation. Sigma by Y is equal to E by R. So this is how you get that expression. Now let us get the second part of the bending equation. Here we go. So this is the neutral axis of the beam, and I'm going to represent the yellow layer, which is A dash B dash, and the blue layer, which is C dash D dash. Now obviously the blue is subjected to tension, so it is subjected to tension. So there is a tensile force that is acting, which is represented by dF. Obviously, yes. I can define the moment of this force about the neutral axis. Moment is force into perpendicular distance. Obviously, the perpendicular distance between the line of action of the force and the neutral axis is y. So is it possible for me to define the moment now, which is going to be the same as the bending moment? For obvious reasons, because they complement one another really well. Just give it a thought. You will be able to understand. So I'm going to define the small bending moment exerted by the blue layer, which is given by the magnitude of the force, which is dF into the perpendicular distance y. So this is the small magnitude of the bending moment that is exerted by the small tensile force above the neutral axis. Okay. Now, if I'm considering another layer, I can also define the bending moment of this force above the neutral axis. Maybe you can call this as dF1. I can call this as dF2. I can consider one more layer, another layer, so on and so forth. And I can also consider layers above the neutral axis, and I can also consider those bending moments. Now, if I want to find the total bending moment, I have to sum all the bending moment exerted by each of these small forces. So this is the bending moment expression for one force. All I have to do is sum all the force. So Newton said, just sum it. But Newton would not write the letter S in this fashion. Newton would write the letter S in this fashion. So Newton said, just sum it. But Newton also has given a shortcut for if you just can express the force in terms of y, then Newton has got a shortcut for integration, for summing. I mean, for summing the forces, for summing the expressions, Newton has a shortcut that is integral calculus. Okay, so here we go. So the expression for bending moment is dm, which is the total bending moment, is given by sum of all the forces which exerts bending moment above the neutral axis, is df into y. In the next step, I can represent the force in terms of stress. Stress is equal to load by area, so load is equal to stress into the corresponding cross-sectional area, which is dA into y. Because if I just take one layer and if I just look at the cross-sectional area of this layer, it's a small cross-sectional area, it's dA. Stress is sigma. You should not be putting d sigma. Please be very careful about it, because you see stress is load divided by the area over which the load is acting. And if you're considering the small force, and you should consider a small corresponding area, so sigma cannot be d sigma. It is wrong. It's a misunderstanding. Okay, fine, it's sigma. So if you just work out for df, so it will be sigma into dA. That's the expression for df. All right, of course you have to integrate it over the limit from the bottom to the top. I'm not just representing that. If you want, you can put minus h by 2, integrate it from minus h by 2 to plus h by 2. Okay, already we have an expression for sigma which we have derived. So sigma is E by R into Y. So I'm going to use that expression. I'm going to plug that here. E by R into Y. Mathematics basically is like moving objects. You just move objects from one place to the other place. Here you're moving mathematical expressions. So Y into Y, it becomes Y square into dA. That's right. So it is M is equal to, Young's modulus is a material property, it's not going to change. Assuming that the radius of curvature is not changing across the length of the beam, you can just pull it outside. Then what is going to happen is you just have integral over y square into dA. All right. Now, what is this expression, integral of y squared into dA? Well, by this time, maybe I can do a separate video for moment of inertia, and this is moment of inertia, which is resistance to bending. Okay, so in the next step, all I have to do is m by I, m is equal to E by R into I. So I can rearrange this expression. I can say it is m by I is equal to E over R. So this is going to be our star equation number 2. Now comparing the star equation number 1, okay, here, and comparing the star equation number 2, I can finally say the expression for bending moment, the expression for bending equation is m by I is equal to sigma over y is equal to E over R. Now, there are some interesting assumptions, there are some interesting interpretations that we can actually make. So if you just take these two expressions and if you try to find the bending stress, define the bending stress is equal to m by I into y. All right. So it's m by I into y. Y is the distance from the neutral axis to the outermost layer. So here is the distance from this is y, it is the distance from the neutral axis to the layer that you are trying to define the bending stress. What if you consider a layer at the neutral axis? If you're considering a layer at the neutral axis, then what is going to happen is y becomes 0 at the neutral axis. So the value of bending stress becomes 0 because y is 0. So at the neutral axis, the value of bending stress is going to be 0. Bending stress is 0 at the neutral axis. So you can construct a beam that is hollow, or you can just fill it with cheap material at the center. If you think that your beam is going to fail due to bending stress, then you can actually replace at the center by cheap material, maybe by wood. We call that as flitched beam. Okay, so just to make sure that you are optimizing materials, you may actually want to do that, but also be very careful. That is, if you keep increasing the moment of inertia, the bending stress that is generated is going to be low. Okay, there is another interpretation. If you're just increasing the moment of inertia of the beam, then the resistance to bending is going to decrease. So sigma can go down if you keep increasing the moment of inertia. Keep increasing the moment of inertia, then sigma can actually go down. No, which means bending stress basically actually goes down. So you may ask this question, okay, in that case, the beam is not going to fail. My answer would be the beam will not fail due to bending stress, engineers, but be very careful. The beam can fail due to shear. So not only you have to find the bending stress for a complete analysis, you also have to do the shear stress analysis. So there are other analysis you have to do, and you have to apply the theories of failure depending on the types of materials before you take smart engineering decisions. Anyway, this is just the basic, and this is mathematicians took 100 years to derive this equation. Keep this at the back of your mind. M by I is equal to sigma by Y is equal to E by R. In answers, if you ask this question whether this is the theory that is running behind, well, there are some advanced theories. For example, you may want to check Timoshenko's beam theories, where the assumptions that were not made in Euler's beam theory is not valid. So shear deformations are also taken into account. You can check Timoshenko's beam theory once you become familiar with Euler's beam theory. This is Euler's beam theory. Thank you all for your patience. Thank you so much.